Hey, this is Leach with Simpson Math, and in this video, we will continue our discussion about solving systems using matrices. In particular, we'll be looking at the Gauss-Jordan elimination technique. So let's get started by reviewing our three matrix row operations. So we can interchange two rows, so just swap them around. We can multiply a row times a scalar s, so s times a certain row, and we'll produce, and I'm using this little lowercase n to represent new row A. And we can multiply row A times S and add it into row B, and then we'll have a new row B. It's important to note whichever row we are adding into, because that is the row which will be the new row. So you can think of it as we're adding into row B to produce new row B. Now when it came to Gaussian elimination, I wanted ones on the main diagonal and zeros beneath. I'm still going to want that same thing with Gauss-Jordan because I do that first, but then once I achieve that goal, ones on the main diagonal, zeros beneath, I then use these ones to make the other numbers above the ones be zero. So the recommended order is that we, again, get this first top left one, use it to make the zeros beneath. Get the next one on the diagonal, use it to make zeros beneath. Get the next one. Then I will use this one and use it to make it'll be the row 2 column 3 number be 0. And then I'm already using that number, so I'll just keep it up and get the row 1 column 3 number to be 0. And then at this point this is 0, 1, 0, so I can easily use this one to make that one be 0. So we're just going to take what we did last time, those 6 steps, and just tack on 3 more and never have to leave the matrix. So in our last video, we saw this system, we turned it into this augmented matrix, and then we performed these 3 row matrix operations and produced this resulting matrix. At this point, we left the matrix and did back substitution, but in this case we're going to stay right there and basically just do the back substitution within the matrix. So you know how we took this is z equals 3 and we back subbed and plugged it in? Basically going to do that, but make this be a 0. So notice that this is a negative 3, so if I could just add 3 to that negative 3, I'll get a 0. So if I multiply row 3 times 3, then then I'll end up with 0, 0, 3, 9. And I add that to row 2, and I get 0, 1, negative 3, negative 6. Add them together, and I get 0, 1, 3 plus the negative 3 is 0, 9 plus the negative 6 is 3. And again, reminder, this is new row 2. So now row 2 has now changed. Row 3 stayed the same, but row 2 is now 0, 1, 0, 3. So notice, what is my y? Well, this is 0x plus 1y plus 0 equals 3. So this is y equals 3. All right, so then basically now we're going to back sub this z into there and then back sub this y into there, but we'll do those on 2 separate steps. So I cannot double up. I'm not allowed to double up and do both of these in the same step. We do have to do these next 2 bits in 2 separate operations. Okay, so I'm going to make this be 0 using this 1. So because this is 1, I just have to multiply times negative 2 to get its opposite. 0, 0, negative 2, negative 6. Just like with the last video, double check. Every time you do that multiplication, check your signs, make sure that every value received it. A lot of times students will do this one, but they'll forget to do the second one. So just double check, don't be in a hurry. All right, so then we get 0 plus 1 is 1, 0 plus 1 is 1, negative 2 plus 2, that eliminates to 0, cancels to 0, negative 6 plus 11 is 5. So I'm going to replace the row 1 with new row 1, 1, 1, 0, 5. So almost there. This equation is x plus y equals 5. The z's gone, but I still need to make that disappear. So if we're basically subtracting the 2, but that's not a valid, look above me. I don't have an option to subtract, but I can multiply one row times the negative and add. Same thing. But always communicate with it this way, but you can kind of casually think of it as subtraction. So negative 1 times row 2. So basically just change the signs. So this is now negative and that's now negative. So 0, negative 1, 0, negative 3, and add. And we end up with 1, 0, 0, 2. And there you have it. Our x is 2, our y is 3, and our z is 3. And that's what we got when we did the back substitution in the previous lecture. So we read it as our ordered pair, or sorry, ordered triple, 2, 3, 3. All right, in our previous lecture, we did this example. So we started with this system, turned it into this augmented matrix. We performed these 5 matrix row operations, and we ended up with this matrix. So let's pick up where we left off, but stay in the matrix and perform the Jordan part of this elimination. So again, the order that I'm working, I'm going to now make this 7/2 be 0. Then I'll make this 2 be 0, and then I'll make, well, whatever this number is then a 0. So if I could just add in a negative 7/2, well, then that will be 0. Conveniently, this is a 1. I can multiply it by whatever I want to turn it into whatever I want. So I'm going to choose to multiply by negative 7/2. So distribute in a negative 7/2. 0, 0, 1 times negative 7/2 is negative 7/2. And the 2's will reduce, leaving a negative 7. So then I just need to add. That stays 0. 0 plus 1 is 1. Negative 7/2 plus 7/2 is 0. They are opposites. And negative 7 plus 9 is 2. And just like we got whenever we did back substitution in the previous lecture, we got y equals 2. So z is 2 and y is 2. All right. So now I need to turn this 2 into a 0. So I'm going to do just that, but multiplying this bottom row by negative 2. Because if this was a negative 2, negative 2 plus 2 is 0. So multiply times negative 2 and distribute. So we get 0, 0, negative 2, negative 4. And then let's add. 0 plus 1 is 1. 0 plus 1 is 1. Negative 2 plus 2 is 0. And negative 4 plus 6 is 2. So now I have 1, 1, 2 up top. All right, one last one to do, and that's to make this 1 be 0. This time though I'm going to use row 2 to achieve that. So I'm going to multiply row 2 times negative 1, so that way when I add them, I get a 0. So I get 0, negative 1, 0, negative 2. Add them up. 0 plus 1 is 1. And we get 0, 0, and 0. So then we end up with x being 0, which is what we knew it would be from our previous lecture. So we get an order triple, 0, 2, 2. Now let's take a look at a new problem for this lecture. All right, let's take a look at this last example. So I have this system here, and with this system, I noticed right off the bat that we're missing a y value in that second row. So notice that's basically a plus a 0y. So I can rewrite, so whenever I write my second row, make sure that you have a 0 in for that value. Now, admittedly, one thing about this example is, again, with all of these, there's lots of different ways to work it. There might be an easier way to work this. When I've worked this one before, I went down some path and the numbers were just getting wackadoodle ugly. So I backtracked and got a little bit more creative. So I'm just trying, the purpose of this example is for you to see that there's lots of different ways to work this. And just to try to give you a few little extra tools about some creativity and ways to look at how to get what we need, how to get these 1s and 0s out of these matrices. All right, so the times that you're going to be the most creative is producing this 1 and this 1. Okay, so keep that in mind. Whenever you get a 1 in the row 1, column 1, and row 2, column 2, and making those be 1s is the time you have to be the most creative. All right, I have this note over here. It says, I need a 1 in row 1, column 1, but I can get a 1 anywhere in column 1 and interchange rows and put it in row 1, column 1. But, as it turns out, I can actually get it directly. But that note is just reminding you that if you find that it's easiest to get a 1 here, like maybe you saw, okay, well, if I just do row 3 times positive 1, so don't change the sign, and just add it, I will then have a negative 1 there, can then multiply by a scalar of negative 1, and now you have a positive 1 in this row. That's a perfectly valid thing to do. It took me 2 steps to get that 1, but actually 3 steps, because I would then need to swap the row to get the 1 in the right spot. So that is perfectly fine. As long as you can get a 1 anywhere, then swap it into place. So on here, I'm going to actually do, take this third row, multiply it times a negative 2, and add it to the first row. So because I noticed that if I do, if I have a negative 6 and add it to 7, I'll then have a positive 1. So there's lots of ways that I could have done this, but that's the route that I've chose. So I'm going to do negative 2 times row 3. So I distribute, check all my signs, make sure it's good to go, and then I add. And then I get negative 6 plus 7 is 1, 10 plus negative 2 is 8, negative 6 plus 2 is negative 4, and negative 20 plus a negative 2 is negative 22. And I replace row 1 with that. All right, so I've gotten a row 1, so I've gotten a 1 in the top left corner, in the 1, 1 spot. Now I'm going to use row 1, column 1, to make these others be 0. So when I do, I'm going to multiply this top row times positive 4 rather, because it's already negative, and then add. So multiply them as positive 4, and we get 4, 32, negative 16, negative 88. Double check signs, positive, positive, negative, negative, positive, positive, negative, negative. Good. So we add, and I get 0, 32, negative 18, negative 94. Woo, getting big. And so we end up with that second row. This one step right here, you are able to do both without rewriting. All the others you're going to have to rewrite your matrix because these two things don't interact with each other, don't interact with the same rows. I can do this. All right, so then again, if I can multiply this top row times negative 3 and then add it to that positive 3, I'll then have a 0 in that place. So let me do that. So I get negative 3, negative 24, 12, and 66. Add them up, and we get 0, negative 29, 15, and 76. Me personally, when I get numbers that are a little bit bigger than this, like big like this, I get a little bit worried. You want to try to bring them back probably to being close to 0, but every problem is different, so in this case, this is how it ended up. All right, so now I have 1 in the top left corner in the 1, 1 spot, and then zeros beneath. Good. My next goal is to make one of these be 1, right? I mean, ultimately, I want this one to be a 1, the row 2, column 2. But if I make that one be a 1, I can then just swap the rows, and I'll be good to go. So I need to evaluate this and try to figure out which way I could do this. So I'm going to do it in a few different steps. I have a note over here. I'm not going to read it to you, but it's basically saying I've tried a few different things. I once tried let's just multiply times 1 over 30. Multiply this row times 1 over 32. I was like, the fractions will be fine later. They just got gross. Promise. Right? So let's follow through with the steps to see about how we can get this to be a 1. All right, I noticed something. I saw it. I was like, whoa, look at this. So if I was to, this is, again, I'm trying to show sometimes you have to be a little bit creative, especially when getting the 1s. I noticed that if I was to add these together, just basically times by 1, because I have to multiply by something. So 1 times row 3 and add them together, and I can replace row 2 with these numbers. And it just so happened that all 4 of these numbers are multiples of 3. So then I could avoid the fractions. I was like, let me just try, because I noticed that this was a positive and this was a negative. and I noticed that this was a negative and that was a positive, and this was a negative and that was a positive. So if I knew if I just added them together, it would make this row just be smaller because those numbers got quite big. They're getting pretty far away from 0. So by doing that, I knew that would bring it down, and it did. It brought it to 0, 3, -3, and 18. And then it was like, oh, perfect, easy. Now if I just multiply row 2 times 1/3, I can then end up with 1. Now, you're not often going to need to do this creative steps, and probably I could rewind this whole process and not have to go this creative. I could probably do something else from step 1 and probably not get such big numbers. But I like this example, like showing this to you just to show you kind of like sometimes a little bit of the creativity that is allowed here, especially like I said, when getting those ones. Okay, so now that I have on this second row my 1 in row 2 column to have a 1, now I can make this 29 be a 0. So to do that, I'm going to multiply row 2 by 29 and then add. So I get 0, 29, -29, and then -174. Add them up, we get 0, 0, -14, and then -98. Fear not, -14 and -98 are actually multiples of 14. So then the easiest way to get a 1 is to multiply by the reciprocal. Now, I tried that up here, but multiplying by the reciprocal produced ugly fractions. But here, it didn't. So that's a, yeah. So, but just know that if you ever need to just force a 1, quickest way is just to multiply times the reciprocal. So -14, I'm going to multiply row 3 times -1 over 14, and we get 0, 0, that's now 1, and divide -98 by -14, and you end up with a positive 7. Once you hit this point, when you've Gaussian eliminated, you're like, woof, really, probably the hard work's done. All right, so now we just need to basically do the back substitution part or the Jordan part. In case you're curious, Gauss and Jordan, these are two different people, two different guys' last name. They've taken credit for it. All right, so we take this this z equals 7 and basically back sub. So I notice that I need this to be 0. So if I add those together, I will then have a 0 in that desired location. So I'm just going to multiply by 1. We have to have that still multiply by 1 because I don't have just an add ability. If you notice, this right here is multiply row and then add. I don't just have an add. So multiply by 1 and then add. 0 plus 0 is 0. 0 plus 1 is 1. That's 0 and that's 1. And remember, we're replacing it. So then I need to make this be a 0. So I'm going to multiply the bottom row times positive 4. So we get 0, 0, 4, 28. Add them together and you get 1, 8, 0, 6. So replace this top one right here with 1, 8, 0, 6. And then lastly, I can use this one to make that 8 be 0 by making this be a -8. So multiply, that is a typo. This should be row 2 times -8. So multiply row 2 times -8. And then we get 0, -8, 0, -8. And we add them together and we get 1, 0, 0, -2. And then so then we end up with our order triple, -2, 1, and 7. So hope this one helped you see that there's lots of different ways to work them. If you get stuck on this path, if you read that paragraph I wrote, like I went down the path, I was like, this is ugly, and I just backtracked and then took a different path. And there's kind of some creative things you can do whenever you find your one. So I hope this gave you a few more tools in your tool belt. And overall, hopefully you understand Gauss-Jordan elimination, how you can solve systems and stay completely in the matrices and be able to be successful in college algebra. Take care, and I'll see you in the next video.